Hello, my name is Henry Eden, and I welcome you to Sethoo Edu TV. For some time now, Sir Harry has been taking you through circle theorem. I'll be taking you through some aspects of maths. I'll be starting with vectors and then continuing with bearing and some other topics, while Sir Harry also takes some other topics. Today, like I said earlier, we'll be continuing with vectors. So then we start with vectors and then we'll continue with bearings and some other topics as well. Now, since we are not going to be asking questions and everything, I'll be putting in some questions at the end of each class so that you all participate in the exercise. All right. So then, vectors, as we have already gone through some aspects in science, we know that a vector is any quantity that has magnitude and also direction. We also know from some things we have also learned in maths that magnitude is the same as the distance as well as the length. So then we are going to take some examples of vectors. We have velocity as an example of vectors, displacement, we also have acceleration, and we have so many more. All right, so then since we have had examples of what vectors are, we can go straight to the point. Now, a vector is usually denoted by capital letters with arrow-headed lines. For example, if we have AB and we want to write this as a vector, then this has to be with an arrow-headed line on top of it, meaning that vector AB. That is to say that the vector from A to B, that is what this vector means. So vector AB is written in this form. All right. Now, going forward, we'll be looking at two different approaches we are going to be using to represent vectors. We have the magnitude bearing form, and we also have the Cartesian component form, which in other words is known as the column vectors. All right. We are going to be starting with the magnitude bearing form of a vector. All right, so we'll be looking at the magnitude bearing form of a vector. Now let's take some examples of the magnitude bearing form of a vector. Now, if you are given this question and asked to represent it, a displacement from the point A to B in the direction of 0, 60 degrees. So we have this. Alright, so displacement from the point A to B in the direction of 060 degrees and a distance of 5 centimeters is written as this. Now this is represented as this on the Cartesian plane. Okay, so this is how the displacement from the point A to B in the direction of 060 degrees and a distance of 5 centimeters is represented on the Cartesian plane. Okay, so I'm going to give one more example and then I'll give you two to try on your own. So example 2. So this one is going to be in this form. Now, since we know that 160 degrees is going to be in this quadrant, it means that the line is going to be drawn this way. We know this is 90 degrees and then this is 180. That is from here all the way to here is 180 degrees. So automatically it means that the 160 degrees is going to be found in this quadrant. Alright? So then this is our x and this is our x and that our y. So from here all the way to here is 160 degrees. And then we are told to find the vector BC. So this is where the B is. That is our vector notation. And this is our C. Alright, so that is it. Now we know it is 4 centimeters. That is the distance between B and C is 4 centimeters. So then the distance is 4 centimeters. That is how it is shown on the Cartesian plane. So then you are supposed to try these examples on your own. I'm going to give you 2 examples to try and then you should be able to do it following these 2 examples. Now before you do these, this representation on the Cartesian plane simply means that the length or the magnitude of AB, that is from the first example, the length or the magnitude of AB is the 5 centimeters. And then the distance, the bearing from A all the way to B is 60 degrees. Now all the time, when you are taking the bearing of a particular point from one point, it starts from the positive y-axis. When we move forward, when we move a little bit forward, we will realize that the y-axis actually represents our geometric north. Our positive y-axis actually represents our geometric north, and that has its own meaning. We'll be looking at that. So then that is it. Let me give you two examples to try and hand at. Okay, so I mentioned two examples, but I've decided to add the last one. Okay, so these are three examples you should try and answer at, and I'm sure you will be able to solve them easily. Just follow the steps I have given earlier. Okay, so that is it. Represent the following on the Cartesian plane. So we are to represent these questions, these distance bearing form on the Cartesian plane. All right. So then when you take PR, remember that this is your distance, that is your bearing. Okay. This one also has to do with the what? Distance and then bearing. So then remember to label everything that I have explained to you to label. All right. So that is it. With that understood and dealt with, we'll be moving on to the Cartesian component form. We'll be looking at the Cartesian component form. In actual sense, this is the magnitude bearing form. I have explained to you how the magnitude bearing form is written. This is the magnitude bearing form. So then, to write the Cartesian component form from the magnitude bearing form is what we are going to do. Alright, so then just like the name goes, the Cartesian plane, alright, the Cartesian plane helps us to get the Cartesian form of the magnitude bearing form of a vector. Or when a vector is given to us, we are going to use the Cartesian plane. With the help of the Cartesian plane, we can get the Cartesian form of a vector. Alright, so we are going to look at it, the Cartesian component form of a vector. when we are talking about the Cartesian component form, we are actually talking about the vector form or the column form. So for a vector to be written in the Cartesian component form, say vector AB, it is going to be in the form x, y, like that. Okay? It is going to be in that form, where the x represents the x coordinate, the x represents the x coordinate, and the y represents the y coordinates. Alright, so it will be necessary to take note of these things. Okay, this is how the Cartesian component form is written. Vector AB equals x, y in the column form. Alright, where the x over here represents the x coordinate, and then the y represents the y coordinate. It is as simple as that. Now, to be able to go through how to write the vector in the Cartesian component form, there are a few things you need to take note of. There's taking the Cartesian plane, there are 4 quadrants. There are 4 quadrants. This happens to be the first quadrant. This the second quadrant. This the third quadrant. And this the fourth quadrant. So under normal circumstances, the quadrants go anti-clockwise, not clockwise. So then this is the first quadrant, this is the second quadrant, the third quadrant, and the fourth quadrant. It doesn't mean that when the question is given to you, when it's supposed to be a number bigger than 90, you go this way. No. When it is a number which is bigger than 90, for instance, when you have 120 degrees as your bearing, it still goes through this direction, because though it is the fourth quadrant, when we are talking about the bearing, it goes clockwise from the geometric north. We will look at that very soon. Now let's look at the first quadrant. Now in the first quadrant, the reason why I'm putting this is for you to note the fact that each quadrant has its special abilities. All right. Now in the first quadrant, we have all the signs, all the trig ratios being positive. So we have sine, tan, and then cos, all being positive. But then when we come into the second quadrant, only cos is negative. The rest are all positive. So we have sin, tan, and then cos. These are positive, but then cos is going to be negative. When we come into the third quadrant, we have, in the second quadrant, only sine is positive. The rest are all negative. Only sine is positive. The rest are all negative. When we come into the third quadrant, only tan is positive. Only tan is positive. The rest are all negative. And we move on to the last quadrant, which is the fourth quadrant. Only cos is positive. Only cos is positive. The rest are all negative. So then we came up with a jargon that we can easily use to remember this, which happens to be, you see, in this case, all of them are positive. But over here, only sine is positive, all right? And then over here, only tan is what? Positive. And then over here, only cos is positive. So then we say that all silly Tom cat. All right. Now we make use of the first we make use of the first variable or the first letter in explaining what is positive in each of the quadrants. In this case, all of them is positive. In this case, only sine is positive, and then only tan is positive in this quadrant, and then only cos is positive in this quadrant. So we have all silly tom cat. That is what jargon we have given to this. All right, so when you are conversant with this, it helps you get the particular sign to apply to a particular trig ratio in dealing with the Cartesian component form. All right, now let's go on to how to get the component form or the Cartesian component form given a vector in the bearing form, in the magnitude bearing form. Let's take a question as an example. Express Okay, so the question is to express the vector AB, which is 5 centimeters and 60 degrees in the component form. This is how we go about such a question. Now, in the first place, we know we are dealing with vector AB, which is 5 centimeters and then 60 degrees. Now, just like we represented this in the on the Cartesian plane, we are going to apply the same thing to this. So let's represent this on the Cartesian plane. Now, this is 60 degrees. So 60 degrees is less than 90. So it is going to be in the first quadrant. Now, this is my y and that my x. Okay? Now, since we are dealing with 60, like I said earlier, it is supposed to be in the first quadrant. So you just draw a line from the center towards that direction in the first quadrant. Okay? Now, we know we are dealing with vector A, B. So this is the direction of the vector. From the y to the direction of the vector, we have 60 degrees. And then the distance between A and B is 5 centimeters. Is that okay? Now, with that dealt with, this alone won't give us the component form, but rather we are supposed to use this in getting the component form. Now, what we are supposed to do is to create a triangle with the x-axis. We create a triangle with the x-axis of the component form. After we have created the triangle, we realize that from here to this part is what? 60 degrees. So if the whole if the whole quadrant is 90 degrees, then we can subtract the 60 from 90 degrees to get this small part, and that is going to be what? 30 degrees. Now, we have this part to be 30 degrees. This, applying Pythagoras theorem and trig ratios all together, we realize that this becomes a right-angled triangle, because since this and that gives us a 90 degrees, it is exactly the same as this. This line here is virtually the same, it's actually the same as this, because if this is a quadrant giving us 90 degrees and we have drawn its mirror line at the other side, exactly mirror to this, or exactly the same as this, it means this also becomes 90 degrees. If this is 90 degrees, we have this length to be 5 centimeters. Once this is 90 degrees, automatically this length here becomes our hypotenuse. So this length is what we call hypotenuse. This angle is what is going to help us find whatever we are looking for. So automatically the side that is opposite this angle is called the opposite. It is called the opposite. And then the last part, which is also adjacent to the angle given, is called the adjacent. So with all the parts known, we can easily find this side, which is the x-axis, and also find this side, which is also the y-axis. So then let's go ahead. I can now clean this and then represent it as the x, and then I can also clean this and represent it as the y, and then the rest can also be cleaned. Now, this is my opposite, this is adjacent, this is hypotenuse. We have enough information to find any of the two. We have the angle given, we have the hypotenuse. So if we are going to use that, then means this is opposite, which is O, this is hypotenuse, which is H. So using the trig ratios, so is the one that corresponds with the information given. So it means we are going to use sine 30 degrees equals opposite, which is y, over hypotenuse, which is 5 centimeters. We can get y by cross multiplying. So then this becomes y equals 5 sine 30 degrees. Because this comes here to multiply, this is like over 1. 1 multiplies y, it gives us y. 5 multiplies sine 30 and gives us 5 sine 30. So then we have y equals 2.5 centimeters. Centimeters because we are dealing with centimeters right from the beginning. So then whatever answer we get has to be in centimeters because we are dealing with the distance from A to X. All right, now let's look at the x. Since we have been able to find the y, which is 2.5 centimeters, we can as well use Pythagoras theorem to find the x coordinate. We can also use Pythagoras theorem to find the x coordinate. That is to say, the hypotenuse squared equals the opposite squared plus the adjacent squared. Okay, nonetheless, we can still use the trig ratios to find the x. So just as we were able to use so, which is opposite over hypotenuse, to find this, we can also look for what to use to find the x. Now this is the adjacent, which is a. Once again, we have hypotenuse, which is h. So it is going to be k, being the appropriate one that suits the information given. So it is going to be cos 30 degrees, and that is equal to adjacent, which is x, over hypotenuse, which is 5. So once again, we cross multiply. This is over 1. So when we cross multiply, we have 5 cos 30 degrees equals x. And that implies x is equal to 4.3 centimeters. 4.3 centimeters. Once again, we are using centimeters because centimeters was given in the question for the distance. So whichever one we get should be in centimeters. Okay. Now, since we have been able to find the y coordinate and the x